At the very basis of life, where molecules and cells run the show, we've discovered machines, literally molecular machines. There are little molecular trucks that carry supplies from one end of the cell to the other. There are machines which capture the energy from sunlight and turn it into usable energy.
There are as many molecular machines in the human body as there are functions that the body has to do. So if you think hearing, seeing, smelling, tasting, feeling, blood clotting, respiratory action, the immune response, all of those require a host of machines.
Studies of the bacterial motor have indeed revealed an even deeper level of complexity, for its construction not only requires specific parts, but also a precise sequence of assembly.
I think design is back on the table. You know, we can't explain these systems by natural law. And if we're searching for truth, and they are in fact designed, if we have to be design engineers to understand them, then I say, what's the problem? You know, you go where the data leads you. And the implications, yeah, they have profound metaphysical implications, but so be it.
Miniaturization, we're shrinking the size of technology at an exponential rate, both wired and wireless. These are some designs from Eric Drexler's book, which we're now showing are feasible with supercomputing simulations. Actually, there are scientists building molecule-scale robots. One has one that actually walks with a surprisingly human-like gait that's built out of molecules. There are little machines doing things on an experimental basis. The most exciting opportunity is actually to go inside the human body and perform therapeutic and diagnostic functions. And this is less futuristic than it may sound. These things have already been done in animals. There's one nano-engineered device that cures type 1 diabetes. It's blood cell size. They put tens of thousands of these in the blood cell. They tried this in rats. Lets insulin out in a controlled fashion and actually cures type 1 diabetes. What you're watching is a design of a robotic red blood cell. And it does bring up the issue that our biology is actually very suboptimal, even though it's remarkable in its intricacy. Once we understand its principles of operation and the pace with which we're reverse engineering biology is accelerating, we can actually design these things to be thousands of times more capable. An analysis of this RESPR site designed by Rob Freitas indicates if you replace 10% of your red blood cells with these robotic versions, you could do an Olympic sprint for 15 minutes without taking a breath. You could sit at the bottom of your pool for 4 hours. Freitas has a design for a robotic white blood cell. We will have 2 to the 25th power greater price performance capacity and bandwidth of these technologies, which is pretty phenomenal. It will be millions of times more powerful than it is today. We'll have completed the reverse engineering of the human brain. $1,000 of computing will be far more powerful than the human brain in terms of basic raw capacity. Computers will combine the subtle pattern recognition powers of human intelligence with ways in which machines are already superior in terms of doing analytic thinking, remembering billions of facts accurately. Machines can share their knowledge very quickly. But it's not just an alien invasion of intelligent machines. We are going to merge with our also go inside our brain, interact with our biological neurons. We've demonstrated.
Using nanotechnology, we create synthetic organisms for healing. This is Sabrina. Sabrina's neurological disorder causes electrical shorts and misfirings between her nerve cells. We created tiny robots called nanites to patrol her body and repair the damage. Sabrina injects herself with 3 species of these synthetic organisms. We enter Sabrina's brain, where her neurons are under attack. All around us, a virus has ravaged her neural nuclei. The virus targets a healthy neuron. An antiviral nanite detects the intruder and moves to intercept it. In another part of her brain, Sabrina's protective myelin sheath needs rebuilding. Tens of thousands of axon repair nanites work together to repair the damage. A nanochip attracts misfiring neurons. The chip synchronizes her neural pulses. The same technology we used to build nanites lets us bring synthetic sentience to life. We are creating an avatar for Sabrina, a self-modifying, continually evolving synthetic organism. As Sabrina and her avatar physical therapist practice Tai Chi, they are bonding, evolving, growing beyond their previous selves. Sabrina's new neural prosthetics have changed her perception of existence. Sabrina is no longer merely Sabrina.
Something 80,000 times smaller than the breadth of a ridge on a fingertip, unlocking a new frontier into cancer research. Nanotechnology, the science of building small, is changing the way we look at cancer. More importantly, the way we look at diagnosis and treatment. Nanotechnology allows researchers to build new tools that are actually smaller than cells, giving them the opportunity to attack cancer at the cellular and genetic level. This technology not only enables health practitioners to detect cancer earlier, but also holds the promise of stopping cancer before it even develops. This revolutionary approach is so precise, doctors will be able to design a unique treatment for an individual's own medical and genetic profile. Based on computer chip technology, diagnostic devices such as nanoarrays are thousands of times more sensitive and accurate than current techniques. Because of their size, multiple lab tests can be done more rapidly and at a much lower cost, using one nano device instead of many. Nanoshells can be linked to antibodies that recognize tumor cells. Once they are taken up by the cancer cells, near-infrared light is applied, killing only the tumor and leaving neighboring healthy cells intact. Scientists are engineering nanoparticles such as dendrimers to seek out and destroy cancer cells. This amazing technology can be customized for targeted drug delivery, improved imaging, and near real-time confirmation of cancer cell death.
In this lab at Wake Forest University, a lab he calls a medical factory, Dr. Anthony Atala is growing body parts.
That's a heart valve. This is an engineered heart valve.
Atala and his team have built from the cell level up 18 different types of tissue so far, including muscle tissue, whole organs, and the pulsing heart valve of a sheep.
And is it growing? Absolutely. These cells are continuing to form new heart valve tissue. When people ask me, what do you do? We grow tissues and organs.
You really are making body parts.
We are making body parts that we can implant right back into patients.
That's an outboard motor. That's designed. That's no chance assemblage of parts.